fx is a piecewise function. So when x is between 0 to a, the graph is going to be behaving in the same way as the graph of y is equal to a e to the power of a minus x. So from x is equal to 0 all the way until a, it is going to be here. When x is equal to a, we have a e to the power of a minus a. So a e to the power of 0 is a, which means that the part of the graph that I'm going to be extracting is going to be from here all the way until here. And according to the domain that is given, x is supposed to be bigger or equal to 0. So here it's going to be a solid dot and strictly less than a. So here it's going to be a hollow dot. And as for the other part of the graph, that is when x is bigger or equal to a for our piecewise function fx, it is going to be behaving in the same way as this graph, except that it is going to be modulus of this. So modulus of this graph will make sure that this portion here is going to be reflected about the x-axis. So we will be getting something that is like this here, and then all the way. And we will be looking for the part that x is bigger or equal to a. This maximum point here, which is a reflection of this point, is going to be when x is equal to a, and y being reflected is also going to be equal to a. So we are looking at from here onwards. So for this portion of our piecewise function is going to be following the behavior of this part all the way until x goes to infinity. It is supposed to be bigger or equal to a, so I have a solid dot here. So now replicating this on my actual graph, which I'm going to be making use of to express y is equal to fx. First part is going to be this. So from here all the way until the point when x is equal to a. And when x is equal to a, y is also equal to a. So I have this. This point here is going to be a e to the power of a, and it is a solid dot. As for this point, it is going to be connected to this point, AA, because they share the same coordinate. But there's a little subtle way to express this part of the graph graphically. That is when the tangent here is supposed to be an angle. So I'm purposely drawing this part such that the tangent still looks like, one that has a particular kind of angle with respect to the x-axis. But as for this part of the graph, the tangent is actually parallel to the x-axis, which means that as I continue from here, the tangent on the right hand side of A should be parallel to the x-axis. So it is going to be something that is like this. Then going all the way until 2A. So here, let's say we have a 2A, then all the way until infinity. And at this point, if I were to take reference to this, it is going to be a hollow dot. But if I were to take reference to this, it is a solid dot, which means that here, it is still going to be a solid dot. I'm not going to do anything to this because this part is supposed to be continuing to this part of the graph. And this will represent my graph of y is equal to fx. And we are supposed to show that f inverse does not exist. For that to happen, it is possible for a horizontal line to cut it at more than one point. So I'm going to use a counter example. I'm going to quote a horizontal line, whichever convenient one I think it is going to be acceptable. And I'm going to make use of just simply the line y is equal to a horizontal line that passes through here. And obviously, it is going to be cutting the graph here and here. That is why I'll give a comment that is something that is like this. Since that the line y is equal to a cuts the graph of y is equal to fx at more than one point. So I know f is not a one-to-one function. And since it is not a one-to-one function, that is why f inverse does not exist. And what we're supposed to do now is to find f inverse, but we are going to change fx to one that corresponds to the restricted domain that we have defined in part 2. And that is when x is between 0 all the way until 2a, and it can be equal to 2a. So for this part of the domain, x is still supposed to be bigger or equal to a, but rather than going all the way until infinity, we are going to be restricting it to less than or equal to 2a, which means that if I were to look at the graph, the new graph that represents this new fx is going to start from here, and it can be equal to 0. X can be equal to 0, so we are having a solid dot here all the way. You will follow the same graph, and here all the way, but it is going to stop at 2a when x is equal to 2a, and it can be equal to 2a. So I'm going to be using a solid dot here. This will be my new graph that represents fx. And to find f inverse, we will be letting y to be equal to fx. But because fx is a piecewise function, so we do need to consider the two sets of domain to that fx is going to be defined. So for the first set of domain, that is when x is bigger or equal to 0, less than a. We know y, which is supposed to be the same expression as fx, will be a e to the power of a minus x. We're going to try to make x the subject. So if I were to ln both sides, I will have a ln y, then ln a times this, which will be ln a plus ln e to the power of a minus x. This, I can bring it forward. So it will be ln y is equal to ln a plus a minus x. If I were to bring x over to the left hand side, we will have a plus ln a minus ln y, which I can also express it as a minus away ln y minus ln a. Combining this together, we have x to be a minus ln of y over a. So this will give us a hint to how the expression of f inverse is going to be like for this set of domain for f. But we do need the domain of f inverse, which is the same as the range of f. Looking at this part of the graph of f, we can find the corresponding range of f. X is supposed to be bigger or equal to 0. So here it's going to be a solid dot. X is supposed to be strictly less than a. So here, if I were to base it on just this portion of fx, it's going to be a hollow dot. So all the corresponding y coordinates will represent the range of f for this set of domain, which means that the domain is going to be strictly bigger than a, the y coordinate. All the way until this a e to the power of a. Solid dot, it can be equal to 0. So here is going to be a square bracket. And we're going to continue to work on the other part of the domain, and that is when x is bigger or equal to a, less than or equal to 2a, which means that y is now going to be equal to modulus of 1 over a, x minus a squared minus a, which is going to be plus or minus 1 over a, x minus a squared minus a. Plus or minus, we can actually choose whether we want to continue with a plus or to continue with a minus. And to make that choice, we will reference it back to the graph of fx. We know we are working specifically on the part of fx where it is going to be between a to 2a. And for this part of the graph, we originally drew it from the graph of y is equal to this without the modulus. And with the modulus, this portion of the graph is reflected about the x-axis. And since it is reflected about the x-axis, which means that if I were to be considering just this portion of the graph, it can be defined by y is negative of this, negative of 1 over a, x minus a squared minus a. And that is why between plus or minus, since we are working on the reflected portion of this graph, between plus or minus, we will choose minus, since this portion is the reflected graph. So it is minus of 1 over a, x minus a squared minus a. Let's make use of this equation, and we will continue to make x the subject. Multiplying by negative throughout, we have a minus y. This is equal to 1 over a, x minus a squared minus a. Multiplying by a throughout, I have a minus ay. This is equal to x minus a squared minus a squared. So x minus a squared, this is equal to a squared minus ay, which means that x is going to be equal to a plus or minus square root of a squared minus a y. And since x is a number that is supposed to be bigger than a, so between plus minus, I'm going to choose plus, so that x can be bigger than a. So this will be a squared minus ay within the square root. And I'm making this choice because x is supposed to be bigger than a, less than or equal to 2a. We will also need to find the corresponding domain of f inverse for this part of the domain of fx. So this is going to be the range of f, and if I were to look at this, x is supposed to be bigger or equal to a, so here it's going to be a solid dot, and less than or equal to 2a, so here is also going to be a solid dot. which means that the corresponding y coordinate is going to represent the range of f, and that is going to be 0, inclusive of 0, all the way until a. And since this is a solid dot here, so it is going to include a. So inclusive of a from 0 to a. So with this that we have found and this that we have found, we now can express f inverse. For the expression of f inverse, we know it is going to be two portions. One is going to be this, from 0, the domain is from 0 to a. So I'm going to write this first, since I will go from 0 to a, then a to a e to the power of a. So let me write this as the expression for the f inverse. So I'll write it as a plus square root of a squared minus ax. This is for x to be bigger or equal to 0, less than or equal to a. As for the other portion, I'm going to go for this expression. So it's going to be a minus ln of x over a. And this is going to be for x to be strictly bigger than a, less than or equal to a e to the power of a. And now we are looking at a over 2, which means that a over 2 is going to be going into the function f, and whatever that comes out from this function f will go into another function f. So the first thing that I'm going to try to analyze is what is the number that comes out from the first function f, and that will be f of a over 2, which means that x is going to be a over 2. When x is a over 2, looking at a function f, which is a piecewise function, we need to decide whether we are going to make use of this expression or this expression. X is equal to a over 2 is between 0 to a. That is why we are going to be making use of this expression. So it will be a e to the power of a minus x, which is now a over 2. So this is a e to the power of a over 2. So whatever that comes out from here, it is going to be of the form a e to the power of a over 2 when the input is a over 2. So now this is going to go into another function f, which means that we got to decide again whether a e to the power of a over 2 is within this part of the domain or this part of the domain. And I think to make that decision, we are going to make use of the fact that a is between 0 to ln 2. The power here is a over 2. I'm going to take this and I'll divide throughout by 2. So I have a 0, a over 2, less than or equal to half ln 2. And since e is an increasing function, e to the power of x is an increasing function, that is why e to the power of 0 is going to be less than e to the power of a over 2 is going to be less than or equal to e to the power of half ln 2, based on the inequality that we have here. And since a is a number that is bigger than 0, so I can multiply a throughout the inequality and it will not affect the inequality. E to the power of 0 is 1, so multiply by a is a. Then here it will be a e to the power of a over 2, less than or equal to, this is going to be a e to the power of half ln 2, which means that this number, a e to the power of a over 2, is bigger than a. Since it's bigger than a, that means x is going to be between a to 2a. So we are going to make use of this particular expression to find f of a over 2, because from the first f a over 2, we have gotten a e to the power of a over 2. So I'm going to put this into the next f, and now like what we have determined here, since this x value is between a is bigger than a that we have looked at here, and we are going to make use of this expression, which means that it is going to be modulus of 1 over a. X is going to be this a e to the power of a over 2, then minus a square minus a modulus, which is supposed to be plus or minus. But from the previous part of the question, we have already determined that for x to be between a to 2a, plus or minus, we can make a choice of minus. So it will be minus of 1 over a of a e to the power of a over 2 minus a square minus a. So I multiply the negative in, minus become plus. So I'm going to write this first, minus 1 over a. I'm going to expand this which will give me an a square e to the power of a minus 2a square e to the power of a over 2 plus a square, which is going to be equal to a multiplying this in. I have a minus a e to the power of a plus 2a e to the power of a over 2, then minus a. So this and this can be cancelled. I'm going to be left with a 2a e to the power of a over 2 minus a e to the power of a. And according to what the question wants me to show, I am going to factorize out a e to the power of a over 2, which will leave me with a 2 minus e to the power of, this will be a over 2. So this multiplied by this will give me a e to the power of a over 2 plus a over 2, which gives me this a. So I have this, and this is what the question wants me to show.